Alright, let's get into section 6.2, so talking about antiderivatives and the indefinite integral. So we saw in the previous section that an antiderivative of 2x is x squared, right? Because we said the derivative of x squared is 2x, so the antiderivative of 2x is x squared. But can you think of another function whose derivative is 2x? Okay, take a second, think about it. Think if you can think of any other functions that when you take their derivative, it gives us 2x. Okay, so one that I can think of would be like the function x squared plus 1. Right? That function also has a derivative of 2x because when you take the derivative of the 1, it turns into a 0. Right? Or I could also think of x squared minus 547. Right? Because again, derivative is 2x and then a 0 on the end there. Okay, you can have x squared plus 1.4397, something like that. Right? You can have all sorts of values here. So what we're really getting at is that if I'm adding this constant term, so whether that's 1, negative 547, 1.4397, whatever that constant term is, it doesn't matter. It's not going to be impacted by taking the derivative, right? Because it turns into a 0 regardless of what it is. So that means any function that has the form x squared plus c is an antiderivative of 2x, right? Where c is just an arbitrary constant. Okay? C is a constant that can be anything. Okay? So if I take the derivative of x squared plus c, I get 2x plus 0, right? Every time. So we get the 2x that we want. This is what we call a family of antiderivatives, because there are actually infinitely many functions here, right? Because you can have x squared plus 1, plus 2, plus 3, plus 4, all the way up to infinity, all the way down to negative infinity, and everything in between. So once we know one antiderivative, big F of x, then all the other antiderivatives are going to have the form big F of x plus c. Okay, so just like with the 2x and the x squared, once I know that one of the specific derivatives of antiderivatives of 2x is x squared, then I can get the entire family of antiderivatives and say that it's just x squared plus c. Okay, so when we take antiderivatives, when we compute them, we just do them with one specific antiderivative, but then we can go ahead and add on that plus c, that arbitrary constant, to include all of the members of that family of functions. Okay? And this brings us to the indefinite integral. So the indefinite integral says if all antiderivatives of little f of x are of the form big F of x plus c, then we write the integral of little f of x dx equals big F of x plus c. Okay, so basically what is this telling us? It's saying that if you compute what we call an indefinite integral, all you're doing is taking an antiderivative. Okay, so this notation here really is just telling us to take an antiderivative. Okay, that's what this tells us. Take an antiderivative, and that's pretty much all there is to that. So we do need to distinguish between the two types of integrals that we've encountered, right? Because we saw before we have the definite integral, and the definite integral is integral with bounds, right, from a to b of f of x dx. Okay, an important thing to note about this one is we interpret this definite integral as area, which means that when we solve it, it produces a number. That's very important. So the definite integral, so the integral from a to b, produces a number. Okay, and then the indefinite integral, so that's just the integral with no bounds of f of x dx. this one does not produce a number. This one produces a family of functions. Okay, so the definite integral with bounds produces a number. An indefinite integral produces a family of functions. This is a very important distinction to make so that we can tell the difference and tell whether or not our solution is really correct, because the first one we're interpreting as an area, so we should get a number every time. That's a physical object, whereas the second one, the indefinite, is just giving us a different function, right? And specifically the antiderivative function. Okay, so let's look at some examples here. So which of the following functions are antiderivatives of f of x equals 8x cubed? So we're checking which of these three are an antiderivative of this function, 8x cubed. So in other words, the derivative of one of these functions, or any of them, is 8x cubed. Okay, so again, antiderivative of this being one of these tells us that the derivative of one of these is 8x cubed. So let's just take the derivative of each of these. So big F prime, 24x squared, that's going to be 48x. So is that give us this? No, certainly not. And then we check g prime, 8x to the fourth, use the power rule. So 8 times the 4, that's 32x cubed. Well, we got the x cubed right, but we didn't get the coefficient right. So this one is also not an antiderivative. Okay, and then let's check the last one. H prime of x. 2 times the 4, using the power rule. 8, we're left with an x cubed. So notice, the derivative of this one is 8x cubed, which means the antiderivative of 8x cubed is this function. So that would be a yes from us. Okay, so the antiderivative, or one of the specific antiderivatives of 8x cubed is 2x to the fourth. So to find the integral of 8x cubed dx, that's just our general antiderivative. So that's going to be 2x to the fourth plus c. So plus that arbitrary constant. All right. So that would be our antiderivative using the indefinite integral. Now, when it comes to actually figuring out how to compute antiderivatives, we have some methodologies that we're going to be working with here. So we're going to start off just dealing with our standard example, right, of x squared and 2x here. And we're going to start to build on that. So we saw that the antiderivative of 2x is x squared. Now, dividing both of these by 2, we would expect the antiderivative of x, so if I divide this, if I divide this by 2, that would give me x, right? And if I divide this by 2, I would expect the antiderivative of this one to be x squared over 2, right? Because if the antiderivative of 2x is x squared, the antiderivative of x should be x squared over 2, right? It looks like it should have that same relationship. So let's check this guess, right? Because we don't know for sure, but let's check it. So let's take the derivative of x squared over 2 and see what we get. So take the power rule, so that's 2x over 2, which is x, which is exactly what we wanted. So the antiderivative of x, right, or x to the first, is x squared over 2. Okay, so let's step that up. What about the antiderivative of x squared? Right, so if we're undoing the power rule here, right, the power rule says I subtract 1 from the power. So to undo that, I would add 1 back to the power, right? So when I'm adding 1 back to the power of x squared, that tells me that my guess would be probably x cubed. I would think that seems like a reasonable guess. But when we check the derivative of x cubed, we see that it doesn't give us what we want. It gives us 3x squared. not just x squared. How can we get rid of this 3? Well, we can do that by dividing both sides by 3. Okay, so the key here is to divide. So instead of just x cubed, let's try x cubed over 3. And say that that's the antiderivative of x squared. So let's check it. So the derivative of x cubed over 3, x cubed over 3, that's going to be 3x squared over 3. 3's cancel, we're left with x squared. So the derivative of x cubed over 3 is x squared. So the antiderivative of x squared is x cubed over 3. All right, so maybe you're able to start picking up on a pattern here, just from a couple of these terms, but the antiderivative of x is x squared over 2. Antiderivative of x squared is x cubed over 3. You might be able to guess the antiderivative of x cubed would be x to the 4th over 4. So we have this pattern appearing here, and it turns out when we're undoing the chain rule, or excuse me, not the chain rule, the product, I'm saying all the wrong rules. When we're undoing the power rule, that's the one. When we're undoing the power rule like this, it turns out that this pattern will always hold, provided that we don't have any bad values in there. So it looks like the antiderivative of x to the n, based on kind of what we're seeing right with this one, it looks like you add 1 to the power and then divide by whatever that new number is. So if I have x to the n, I would add 1 and then I would divide by whatever that number is. So x to the n plus 1 over n plus 1. Let's check that. Let's see if this actually works. So the derivative of x to the n plus 1 over n plus 1. If we can get x to the n, then we're golden. So use the power rule, bring down the n plus 1 times x to the n over n plus 1. Notice we do get that cancellation there, and that gives us x to the n. So we do, in fact, have a valid antiderivative here. So what that tells us is the integral, the indefinite integral of x to the n dx equals x to the n plus 1 over n plus 1 plus c, right? Plus that arbitrary constant. And this is all assuming that n is not equal to -1. We cannot have n equal to -1 because, as you can see down in the denominator, that would give us a 0, and we can't have a 0 in the denominator. Okay. So what about a different type of function? What about the antiderivative of f of x equals 5? Just some constant function. So think about this kind of backwards. So think I had a function and I took its derivative, and its derivative gave me 5. What must that original function have been in order for that to happen? Well, we know that the derivative of 5x is 5. So we can say that 5x must be an antiderivative of 5. Is an antiderivative of 5. Notice I say it's an antiderivative. It's not the only antiderivative. It's one of them, right? It's a member of that family of functions. So in general, if k is a constant, the derivative of k times x is k. So the antiderivative, the integral of k dx, is kx plus c. Alright, so if we take the antiderivative, or the integral, of k, just some number, some constant, we get k times x, right? And then plus that constant c. Alright, let's look at another one. So find the integral of 3x plus x squared dx. So let's use some of the information that we've already found. We already know some of these. So, for example, we know the antiderivative of x, and we know the antiderivative of x squared. We already found those. So we know antiderivative of x is x squared over 2, right? We found that earlier. And antiderivative of x squared, we also found that earlier, that was x cubed over 3. So, the integral of 3x plus x squared dx equals 3 times x squared over 2 plus x cubed over 3 plus c, plus that arbitrary constant. Okay. With these antiderivative problems, always a good idea to check. Okay, just check and make sure that when you take the derivative of your answer, it gets you back to where you started, to that original function. So let's just take the derivative real quick of 3x squared over 2 plus x cubed over 3 plus c. Take the derivative, that's going to be 6x over 2 plus 3x squared over 3 plus 0, which is 3x plus x squared. Okay, so let me separate this off here. Okay, so we did get back to that original function that we started with by taking the derivative. So that means that this was the correct answer. So that's our valid solution there. Okay. A couple properties about the indefinite integral, just integrals in general, that we need to know. If we have the integral of f of x plus or minus g of x, so if we have a sum or difference of functions in an integral, you can actually split those up into two separate integrals, right? Or as many integrals as you need to in order to do that. And then if you have an integral of a constant times a function, you can pull the constant all the way out of the integral. Okay? And if you want to think about it, right, these are just antiderivatives, and derivatives allow us to do these things. So hopefully it makes sense that the antiderivative also allows us to do these things as well. Okay? So you can split up across addition and subtraction, and you can pull out constants. So let's look at a few examples right here. So the integral of x to the 5th dx, well, we're undoing the power rule, so we're going to add 1 to the power, divide by that number, x to the 6th over 6, and then plus c, that arbitrary constant. Okay. And then next up, t to the 8th, so different variable, same type of solution. Undo the power rule, so that's add 1, so t to the 9th, over that same number. So t to the 9th over 9 plus c. Okay. Integral of 12x cubed dx. So for this one, undo the power rule, so that's 12 times x to the 4th over 4. Right, add 1 to the power, divide by that same number. The 12 and the 4, there's plus c as well. 12 and the 4 have some cancellation, so that's just 3x to the 4th plus c. Okay, I can box these as we're going along. And then the last one here with some q's in it. Okay, this one you could use the properties up above that we had just talked about, right? You can split it up across the addition and subtraction. You can pull out the constants. But this is going to give us, right, q to the 4th over 4 minus 6 times q cubed over 3 plus c. A little bit of cancellation in that second term, so let me just rewrite that. The 3 cancels. There's a factor of 3 and the 6, so we're left with just a 2 q cubed on that one. And that would be our general antiderivative there, our indefinite integral. Okay. So for some antiderivatives, we do have procedures like this one, like the undoing of the power rule. Other ones you're just going to need to know. So here's a few additional common antiderivatives. So the integral of 1 over x dx. So we had a function, we took its derivative, and it gave us 1 over x. Can anybody think of what that function would be? Right? The derivative of this function is 1 over x. What is it? So that original function would be the natural log function. So this would be ln, except we do need to make it ln of the absolute value of x plus c. The reason we include absolute value is because if we're starting here with the ln must have a positive input inside of it. However, if we're starting over here, that x could be negative. And if that x is negative, we need to be able to make it positive for ln to be valid. So it's ln of the absolute value of x is our antiderivative there. But do note that we could have the integral of 1 over x dx is ln of x plus c with no absolute value if we know that x is positive. Okay, so if x is greater than 0, we don't need to worry about the absolute value because it's already positive. Okay, but in general, we just leave the absolute value on there just in case it's negative. Antiderivative of e to the x, well, the derivative of e to the x is e to the x, so the antiderivative of e to the x is also e to the x plus c. Okay. Now, what if we have a function like e to the kx, right? Well, to find the antiderivative of this, so your first guess might be, so you can write this down or you don't have to, your first guess might be, okay, well, I think it's just e to the kx again. But then when you take the derivative of that, you're going to get e to the kx times the derivative of the inside because of the chain rule, so that's going to be times k. And then we look back at this and we say, wait a second, there's no k here. What happened? Well, we need to get rid of it, and we do that by dividing it away. Okay, so we're going to go ahead and divide this solution by k. So we get 1 over k times e to the kx plus c. Okay, so dividing by k helps undo that little bit of chain rule, that bit of the inside function there. Okay. Next up, integral of cosine. So we had a function, we took its derivative, it gave us cosine. What was that original function? It was sine of x, because the derivative of sine is cosine. So the antiderivative of cosine is sine. Okay. And then similarly, if we have cosine of kx, right, that extra constant inside the function, then we can go ahead and just divide by k to undo its effects. Oops. Plus c. Okay. So if you have that constant multiple inside the function, you can divide it away to undo its effect on the antiderivative. Okay. And you can always check it. Again, always a good idea to go back and just take the derivative of your result and make sure that it matches with your original. Okay. Antiderivative of sine, before you're too quick to just say cosine, we had a function, we took its derivative, it was sine. The derivative of cosine is negative sine. Right? So the antiderivative of positive sine would actually have to be negative cosine of x plus c. Okay? Because the derivative of negative cosine is negative sine. So that becomes positive sine, which is what we're looking for. Okay? And then similarly, if you have, again, that constant on the input, you can get rid of it by dividing by k. Don't forget this is still negative. Cosine of kx plus c. Alright, so these are just a few. We'll see plenty of antiderivatives as we're going through the chapter, but these are just a few of the more common ones that you could see popping up in problems. So let's look at this example here. So here we have a bunch of terms kind of all strung together. So what we're going to do is utilize those properties of the addition and scalar multiplication we saw earlier and combine them with all of these antiderivative properties we just talked about. So first off, we can split up across addition and subtraction. So split here and here. So we're going to get three separate terms, three separate integrals. Okay, the first integral, notice I can pull the 3 out of it. So I'm going to get 3 times the integral of cosine of 5x dx plus integral of 1 over x dx, nothing more I can do to that one, minus, notice the 4 here, I can pull that out to the front, integral of e to the 2x dx. Now we can go ahead and compute the integrals individually. So integral of cosine of 5x is 1 over 5 times sine of 5x. Okay, so the 3 is still there, so that's actually going to be 3 over 5 times sine of 5x. You don't need to add a plus c to all of these. All of the plus c's will just kind of combine at the end. So we'll just leave a plus c off until the very end of this calculation. Okay, antiderivative of 1 over x, we saw that just up there, that's ln of absolute value of x, and then minus 4 times antiderivative of e to the 2x is 1 over 2 times e to the 2x. So 4 over 2, that's just 2, e to the 2x, and then plus c, plus that arbitrary constant. And that's going to give us our full, pretty lengthy answer there. Alright, so that's kind of combining those properties.